All right, in the first two videos we talked about intermolecular forces. Now we're going to talk about how those things affect phase changes, basically solid, liquid, gases. Yes, plasma is a phase, but it doesn't come up in chemistry, so we're going to ignore it. Okay, so the three phases are solid, liquid, which I guess in my notes is over here, and gas. Okay, here's how I describe solid, liquid, and gas. I literally use my hands. A solid, what happens is you have strong intermolecular forces. It's held together very tightly. It can't move. So this is one molecule, this is another. They hold together very strongly. A liquid, those intermolecular forces, there's either enough heat to overcome those intermolecular forces, but they're still kind of holding together, so they can move around, but they're still touching each other at all times. Okay. Gases, you provided enough energy to completely overcome those intermolecular forces, and they're able to flop around. So if you have a molecule, the colder it is, the less likely it is to overcome the intermolecular forces, and it'll latch together and basically be a solid. If you provide some energy in the form of heat, it'll form a liquid, and it'll be able to move, but not very well. If you provide enough heat, it'll overcome all the intermolecular forces, and it'll just pop apart and fly off and do its thing. Okay. So what we need to talk about real fast, this is not a huge deal, most of these things are pretty much common sense, but we need to learn what the different phase changes are, what the name of them are. Okay, so going from a solid to a liquid is melting. Presumably you've heard of this one. Okay, and going from a liquid to a solid is freezing. Yay, nothing complicated yet. I say yet because it's going to get complicated. Going from a liquid to a gas is sometimes called evaporation. In most chemistry textbooks, they call it vaporization. Same idea, same root word. Okay. The opposite, going from a gas to a liquid, if you take a gas and you cool it down and it becomes a liquid, that's condensation. Okay. It is entirely possible to go from the solid phase to the gas phase without passing through the liquid. It requires some weird conditions, and later in this chapter we are going to talk about that. That is a process called sublimation. Can't draw a straight arrow apparently, but that's okay. Sublimation is kind of weird. Actually, it looks really, really cool. Most molecules don't do that at like atmospheric pressures because there's a pressure and a temperature component to this. The opposite of this is something called deposition. We need to talk about all of these. Okay. Most textbooks, for some reason, start with vaporization and condensation, so we're going to start with that. Okay. So, because I talked about the fact that you need energy to overcome these things, it turns out that enthalpy is critically important to this stuff. So, last semester we talked a little bit about enthalpy changes, and delta H, and all that stuff. It's not going away. Unfortunately, most of the stuff from Chem 1 never goes away. Sorry. So, we want to know how much energy does it take to go from a liquid to a gas for any given compound. And this is something called the enthalpy of vaporization, which is usually labeled as delta H of VAP. Okay? It's not real complicated, honestly. Let's just look at an example. So we talked about water in the last video. If you have water as a liquid and you add some heat, you get water as a gas. Basically, you go from liquid water to steam. Okay, you're basically causing a phase change. It's still the same molecule. It's not like a chemical reaction. Okay. For this particular molecule, it turns out that delta H of vaporization is equal to positive 44.0 kilojoules. Quick review, as far as this enthalpy value, if it's positive, this means you have to pump in energy. If it's negative, you're going to release energy. It makes sense that we have to heat up water to get steam, so that's a positive value. Okay. This is how much energy it takes at room temperature, which is 298 K. If you have a container of water and you just leave the lid off, it will eventually evaporate. Okay, it takes a long time because this much energy isn't just floating around all the time. Focus, focus. All right, isn't floating around all the time. But there is enough energy that if you wait long enough, it'll eventually absorb enough energy to evaporate all the molecules. Okay. It turns out, because chemists are lazy, that we don't usually have like a table of vaporization enthalpies, or enthalpies of vaporization, and then also a separate table of enthalpies of condensation. They're literally the opposite. We learned with Hess's law that if you reverse a reaction, you get the opposite sign. So if you have condensation, it's literally exactly the same thing in reverse. And we're just going to think of it like that. So if you have H2O gas becoming H2O liquid, the delta H of condensation is equal to negative 44.0 kilojoules. Okay, so what I will tell you is that if you look in a textbook or if you look online, you'll almost never find a table of enthalpy of condensations, but you might find a table of enthalpy of vaporizations, because it's understood that if you have this one, you can easily get this one by understanding that they're the reverse of each other. Okay, so I don't know, let's try an example that has the stuff in it. We've seen enthalpy stuff before, but I just want to make sure you've got a fresh example in your notes. Okay, so we want to know how much energy is needed to evaporate 175 grams of methanol, CH3OH, okay, at 298 Kelvin. Well, we're going to need the enthalpy of vaporization for that. Okay, delta H of vaporization for methanol is equal to 38.0 kilojoules per mole, or just kilojoules, whichever way. Some textbooks write it some way with per mole and some don't. They mean the same thing though. What this means is that 1 mole of methanol will require 38.0 kilojoules of energy to convert. Before we actually do this problem, I actually want to point out something between these two values. So for methanol, the vaporization value is 38.0 kilojoules, and for water, it's 44.0. We looked at boiling point in the last video to look at trends for strength of intermolecular forces. Both of these molecules are somewhat polar, and both of them can somewhat form, or they can also form hydrogen bonds. So the types of forces are the same. But what we see is that the amount of energy needed to break apart the water molecules to form a gas is higher than for methanol, which means the intermolecular forces in water are stronger than the intermolecular forces in the methanol, even though they're the same type of forces. Okay? These are the type of trends we need to be able to spot while we're thinking through this stuff. All right, let's try the actual example. So what we know is that it takes 38 kilojoules to convert 1 mole from liquid to gas. That's what vaporization means. We don't know if we have 1 mole, so let's find out how many moles we've got. 175 grams of methanol. And what you do is you add up on the periodic table, which you add up a carbon. There's a total of 4 hydrogens and an oxygen. When you add that all together, you get 32.042 grams per mole. Okay? Your grams are going to cancel out. You'll end up converting it to moles. And I'm just going to do this all as one problem. We know from this that it takes 38.0 kilojoules per mole of methanol. So if we cancel everything out, that will give us kilojoules. And the answer comes out to, so if you take 175, I guess I'll show my work here. So if you take 175 divided by 32.042 times 38, I got 207.5. This has 3 sig figs, so 208 kilojoules of energy. Okay. Nothing too crazy, nothing that we haven't seen variations of before. Okay. Okay. We need to still talk about vaporization, but we need to talk about the fact that this requires heat sometimes. Yes, you can just leave the lid off of something and it'll just evaporate, but honestly, the easiest way to convert something from a liquid to a gas is to heat it up, to boil it. Okay, so we need to introduce the concept of vapor pressure. Okay, so if you have a liquid in a container, and there's some top of the liquid here, what you'll find is that if there is enough background energy to overcome the amount of energy or the amount of kilojoules per mole needed to evaporate this stuff, for almost every liquid, you're going to end up with some of this stuff being in the gas phase above it. This is the vapor, the fumes, okay? And in general, the idea is the stronger the intermolecular forces, the more likely it is to be in the liquid phase. Remember that what's happening is you have to overcome, so in a liquid phase it looks like this. If you have to overcome this, you're going to need more energy, you're going to need weaker forces, okay? So if you have strong forces, it's more likely to stay in the liquid phase. If you have weak forces, it's more likely to end up in the vapor phase. So what this means is, we said that water is 44.0 and methanol is 38.0. We would expect methanol to have more vapor above it, have more fumes than water. Okay, seems easy enough. So let me write some of that down. So stronger intermolecular forces means it's going to have a lower vapor pressure. I can't write legibly, sorry. Lower vapor pressure. And the opposite of that is also true. If you have really weak intermolecular forces, it's going to evaporate very easily. Okay. The amount of vapor goes up if you increase the temperature. Okay, because it makes sense. You're overcoming these. You have energy. You have enough energy to overcome these forces. Okay, so vapor pressure increases with temperature. Okay, and being a chemist, we're going to make a graph. This is something called a vapor pressure curve. Okay, and what we do is we plot vapor pressure versus temperature. Turn this so I can write legibly. So vapor pressure will increase that way. So what we mean by vapor pressure is just how many molecules are in the gas phase, okay? And we would expect, we just said that vapor pressure increases with temperature, so we're gonna expect it to be an upward trend. It turns out for most molecules, so for something like water, what we find is that it kind of actually forms a curve. It's not a nice straight line, which would be convenient, but we don't have that. So it is what it is. Okay. So what we find is that as you increase the temperature, there's going to be more and more vapor particles, more and more of the water in the gas phase. Okay. And what's going to happen is at some point you're going to cross this line where, let's see if I can draw a straight line here, where you cross the atmospheric pressure, 1 atmosphere or 760 millimeters of mercury or whatever the background atmospheric pressure is. This should be the boiling point. Okay. Okay, so this little dot here is the boiling point. Okay. A couple definitions. I'll see if I can squeeze them into this little space I've left myself. I know I already mentioned boiling point in the last video, but we really didn't explain what it was. Boiling point is where the vapor pressure is equal to the surrounding atmospheric pressure. So if I asked you, what is the boiling point of water? You would say 100 degrees Celsius or 212 Fahrenheit if for some reason you're stuck on Fahrenheit. Okay, that is true if the atmospheric pressure is 1 atmosphere, which is typical atmospheric pressure. That is known as the normal boiling point. Basically, the normal boiling point is the same as the boiling point, but it's at 1 atmosphere. It is entirely possible to boil water not at 100 degrees Celsius. Okay? Honestly, you have to have really specific conditions for it to boil at that. It's basically just where it intersects on this curve. But if you were up in the mountains, so lower atmospheric pressure, so if you lowered this line, what would happen is the vapor pressure would equal the atmospheric pressure at a lower temperature. Okay? So boiling might be like 90 degrees or 85 or something, I don't know. Depends on how high up you are. Being in a mountain in the Appalachians is not the same as being at like Mount Everest. Okay, but the idea is the water would start boiling, it would start bubbling and looking like it's boiling, but it wouldn't be 100 degrees. And honestly, no matter how much you heated it, it would not get above 100, it would not even get to 100 degrees. It would get to that point where it boils and then it stays there. Okay, this is why if you ever look at instructions, cooking instructions on like boxes of mac and cheese, it says at higher elevations boil it for longer because you're not at the same temperature. You might be boiling water, but it's going to be at a lower temperature, so you have to cook it for longer to get the same effect. Okay, boiling is a complicated concept. I know it's like, oh, this is the temperature I need to memorize, but there's like a curve happening underneath of it. Okay. Dense, weird, complicated stuff. Okay. We'll talk more about this stuff later. Thanks.